talked about this before. When we start thinking about how electricity moves and how we can use it, there's three basic concepts that come up. The first one is something called current. Okay, and that is electricity that is moving. And for what we're doing here, we don't want to know that the electricity is just moving. We need to know how fast it is. So it's expressed as a rate. Think miles per hour, gallons per minute. Okay? At this level, electricity is often pictured as moving like water. All right, so I go out into the shop sink, I turn that faucet on, water is running out of the faucet, that's current. Okay, and we can measure how fast it's moving because I can put a bucket underneath, hit a stopwatch, and just time it. And after a minute, I can figure out how many gallons of water I'm filling up per minute, which is the standard measure of water speed used in all sorts of things, from sprayers to water systems for towns and rural networks. Electricity has something similar. We call that the current. Okay, now to get that current to move, it's not going to be able to move by itself. It needs a push. We call that push in electricity voltage. I'm just going to abbreviate electricity there. And that is to push to get electricity to move. Water goes through the same thing. Okay, here in Millbank, a lot of that water is being pushed by gravity. The water is uphill, say out in the Coteau or something like that, and just gravity pushing on that water as it's being pumped out of the ground and put into those water pipelines. We turn that faucet on the other side of the door. Gravity is what's pushing that in. Okay, that's how my water is delivered. I'm on rural water there. If you live out of town and you're not on rural water, you're having an electric pump that is doing the same job for you. It's pulling water out of a well. It's also putting it under pressure so it'll actually go to your house, to your barn, to your farm shop, whatever the case may be. Okay? In water, we measure that push as pounds per square inch, PSI. Okay? Here, it's called voltage. And we can get into the really nitty-gritty of this, but it gets in. Once you really start studying it, it gets into quantum theories, and I don't understand quantum theories very well. Okay, so I'm not going to go there. Now, we have electricity moving. We have that push to get the electricity to move. There is always going to be something that's going to try to get in the way, and we call that resistance. And this is something to slow down or stop electrical current. Okay, that can be shown as a couple of ways. It can just be part of the system. I've mentioned this before. So it could be copper wire. It could be aluminum wire. Silicon, what computer circuits are made out of, or chips, I should say. That would be a better explanation. But electricity isn't just always flowing around. I mean, in nature, when do you see electricity? Lightning. It's pretty much it. Okay, and that's instantaneous, right? So when we use electricity, as soon as you generate it, it wants to dissipate. And what we do is that we generate electricity and we try to hang on to it long enough so that we can use it for something. Okay, and the reason it's like that is because in nature there is a lot of resistance to having electricity move. Everything resists electrical flow to some extent. And that's because of Newton's laws of motions. An object at rest tends to stay at rest, right? Same thing here. And that's why you need voltage, because without it, you don't get any current. Yes, sir.
Is that why we chose to make wires out of copper?
Exactly, because copper wire has less resistance to electrical flow than aluminum does. Although aluminum wire, to make wire out of aluminum is much less expensive, it is used in certain applications. Copper is a much more efficient choice. Okay, so it's part of the system. It is the load. What is the electrical load? What are you using the electricity for? So it would be things like chargers, motors, anything that's consuming electricity would be considered a load. Those are going to, as they're using electricity, they will have some resistance in them as well. Okay, with resistance, there's always heat. Always, always, always. Unless you start getting into the superconducting materials, but that's beyond the scope of what we're doing here. But that is just one of the natural results of using electricity, is that you will generate some heat when we're using these things. The question is how much heat can a device take or a wire take before it melts apart or breaks down or something along that line. That's why if you're using your phone charger and your phone charger is warm after you unplug it, or you're using your phone and for some reason, like my phone does this too, is I'll pick that phone up and my Lord, it's hot. Well, something is causing it to process like crazy. I've got Google Maps running in the background, or something is really drawing on its resources. That takes a lot of electricity to run all that processing. When it's working really hard, the phone gets hot. Okay? So, current, voltage, resistance. Current is moving electricity, and we give it a rate, so it's speed. We have a push to get the electrons moving, that's voltage. And then in any system, there is going to be a resistance to that electrical flow. Partly because that's just the nature of the materials, partly because we're actually using it. And that device is going to have some resistance in it as well. And whenever we have resistance in a circuit, there is going to be some amount of heat that's going to develop in it. Might not be much, but there'll always be some. Okay? Clear as mud? All right. Next thing then, is that these three items are related, and they're called Ohm's law. And the formula for Ohm's law is really simple. If we're looking for voltage required in a circuit, we're going to take the voltage, and that will equal the amount of amps or amperage, and I just spelled that wrong, in that circle, or circuit, excuse me, times its resistance in that circuit. All right, to shorten things up, we usually don't write this all out. We'll abbreviate voltage with the letter V. Amps will show up as a bunch of different ways. I might do it that way. I might have it written out like this. Might use the letter I. That's actually really common. Why the letter I? Honestly, I don't know. Don't know off the top of my head. I'd have to Google it to find out. Resistance, the unit that they use for resistance is the ohm or ohms. And then the symbol that's often used is, I think that's the Greek omega sign. Is it? Okay. Or they'll use that. Okay. Amperage times resistance equals the voltage. Well, if we know that that's our arrangement, then if I have two, I can figure out the other. This is the setup that makes it work the easiest. Is if you draw that out, and if I need to know the voltage in a circuit, I cover up the V, and then it's amperage times resistance. If I am trying to figure out how much amperage is in a circuit, I cover that up, and now I take the voltage and divide it by the resistance. Same thing going that way. If I need to find the resistance that's in a circuit, but I can measure the voltage and I can measure the amperage going through it, I just divide those two out. And that is the basic and the basis of everything that is electrical in nature. From here, we can figure out actual power, and then we can compare it to horsepower. I can compare motors. I can figure out battery capacities in life. I can figure out how to charge for electrical use. But this is the basic behind it. Okay. Any questions? So far, so good, right?